Well, good morning and welcome back to Math 168. In this episode, we are going to talk about the thrilling world of understanding and interpreting a confidence interval level. So, in a confidence interval level, we are really looking for an interval. And this interval of confidence, as we say, is really an estimate. We're going to talk about looking at that interval of estimate and basing that on a margin of error, because we've discussed a margin of error before. And we know that a margin error is equal to two standard errors, left and right. We're going to talk about this confidence interval. We're going to talk about the 95% confidence interval to be specific, and using an SE in order to calculate that. We're going to helpfully understand the confidence interval and take a look at some common misrepresentations. So here goes a statement that's made. A report from a Gallup poll in 2011, based on some random samples of 147,291 adults, says, we believe that 45% of American adults reported get their health insurance from an employer. This would be a common type of statement you might see in a newspaper, in a magazine article, on the internet. And the question for us is, how accurate is this 45%? That's really what we're looking at, what we're talking about. So how do we take a look at that? How do we actually test that? Well, that's what we want to do at the beginning. So first of all, we don't know the true proportion for the population. We don't know if all Americans are actually 45% or if all Americans are 48%. We really don't know. We need to estimate the interval, meaning we need to come up with a range. And how do we do that? Well, we look at a statistic, and we take a statistic and we plus or minus a margin of error. We give ourselves a window. The question is, how do we determine this margin of error piece? We can find the statistic. The statistic is the 45%. What we want to know is how far above and how far below the 45% can we go and still be within inside of the margin of error, or, as we're going to state, the confidence interval. So the interval estimate gives us is a plausible range, and it's a plausible set of values is really what it is. And it's a value for the population parameter. And remember that when we use the word population parameter, when we talk about that, remember that's the statistic of the population that describes the population, whether it be a mean or a proportion or a row value. One common form of an interval estimate is to take the statistic and add or subtract the margin of error. So if we know the actual margin of error, we will push it out onto each side, we'll add it, and we'll subtract it. It says the margin of error reflects the precision of the sample statistic as a point estimate. I'm going to highlight that point estimate because you see those words often in upcoming assessments. And when you see those words, that point assessment really reflects to that sample statistic. Those sample statistic and a point estimate are the same thing. And it's a point estimate for the parameter. If we need to construct a 95% confidence interval, we'll use the statistic plus or minus 2 times the standard error. So if we don't have the margin of error, we'll just simply slide in the standard error and we'll multiply it by 2. Hint, the statistic could be a mean or a proportion of a sample. So when we take the statistic, it comes from the sample. When we lead it to the point estimate, we're talking about the parameter. Because remember, we don't have a sample statistic for the parameter. So getting back to this question, it says 45% of American adults reported getting their health insurance from an employer. Later in the report, it says the maximum margin of sampling error is plus or minus 1. Okay, so now it starts to get into a little bit more detail for us and tell us a little bit more about what was going on with it. So what does that mean for us? Well, what that means for us is that, and let's make this large, let's make this full screen right now. If we have a statistic, and we're going to add and subtract a margin of error, and right now we're given a point statistic of 45%. And now we're given a margin of error 1%, because it says 1% up, 1% down. That means that our confidence or our margin of allowable movement is going to be between 44 and 46%. So what we're building is really an interval estimate. And in our case right here, that interval estimate comes out to be exactly what I just said, 44, 46%. The percentage of American adults getting their health insurance from an employer is probably between 44 and 46%. This would be a typical statement that you might need to make in response to any question on an assessment or in your homework. So how do we determine the margin of error? It says we can use the spread of the sampling distribution, the standard error, to determine the margin of error for a statistic. So inside of, wrong way, inside of StatKey, if we were running a confidence interval level, let's just say for a single mean, and let's say we ran this a couple of thousand times here, whatever this data is, we have a standard error right here, 2.219. So I could take my original statistic, and my original statistic over here is 15.98. That's my mean. And I could add and subtract 2 of these standard errors and have a good working confidence interval level. A confidence interval for a parameter is the interval computed from the sample data by the method that we will capture the parameter for a specific proportion. Okay. The success rate is the proportion of samples whose interval contains that parameter, known as the confidence level. So what that means is, if we say that we have a 95% confidence interval level, it will contain the true parameter for 95% of all samples. If we run that sample 100 times from the sampling distribution that we do, 95% of the samples will actually catch that parameter of that population. And I'm going to show you a picture of what that means here, and then I'm going to go do it for you, because it's kind of different to look at it and different to see it. On the right-hand side, each one of those is a test. Okay, so a draw back in and get an average or get a population or get something. Okay, so the green bar means that the interval, and you can see how it has width to it. The width of the interval is the low, maybe think about the 44% we just did a second ago, and the high is the 46% we just did a second ago. Dead on the middle is the 45%. Well, this black line represents the true proportion of the population. And the true population of the proportion, the green bar caught it. Even since this is not here, since this test was a little above 45, let's say it was 45 and a half, it still was within the range. All the greens are still within the range, no matter how close they get to the edge. The reds are not within the range. And I'll show you that outside in StatKey how that actually works. So I'll go out here and I'll go to a sampling distribution, and I'll use a proportion. And the proportion that I actually have is 275. So I think I'll edit the data. No, I won't edit the data. I'll just leave it. It's a 275. It's easier just to simply roll with the one that we have here. So if I run this test, and let's say I run this test one time. Now I'm going to switch over, first of all, to confidence interval. So here's going to be those green bars. I'm going to run one test. And enter a valid proportion. Great. There we go. Let me rerun. It always wants to mess with me. Proportion, confidence interval level, generate one sample. Boom, got one. Okay, let me go here. So look, the green bar, it got one. In this particular one, it caught it. It was within inside of the confidence interval level. And what that means for us is that the lower range and the upper range caught the true population parameter. Remember, my true population parameter was 275, and you can see it listed right there in the middle at 275. Let's run it one more time. it missed. So this time we have a miss right away. So this one was way off. The higher end here, the actual number was 185, and 185 did not fall within the confidence. So it didn't hit. It misses. And I do it again and again and again. Oh, I got a couple of misses. So if this is a 95% confidence interval level, what we're saying is if I run this 100 times, by the time I do this 100 times, I should have only 5 misses because it should catch the true population parameter 95% of. I'm going to generate 1,000. And you can see how dense they are. But up here, you can see the proportion is 95.41. So it actually hits that proportion very nicely and actually a little bit above it. So the interval depends upon the confidence itself, okay? And we don't always have a 95% confidence interval level. We do change sometimes to 90, 98, 99. Now here's a nice statement, and make sure we are good on this statement. 95% confidence interval states that if the sampling distribution is relatively symmetrical, meaning that when we have a nice curve here, we have a good set of symmetrical data, relatively symmetric. And it is bell-shaped, that a 95% confidence interval level will be estimated using statistic plus or minus 2 times the standard error. Again, when I run my distribution and I go back to my data was 0.275. 0.275 plus or minus 2 standard errors. So my confidence interval level for this particular piece, and I'm going to write this down and then we'll do the math. So I'm going to multiply 2 by 0.032. So I'm going to turn my camera on so you can see it. I had to write my numbers. Tell you what, let me do this. Let me minimize. Let me do a little Windows effect here. And let's grab this one. That way you can see both things. So I took the original 0.275 and I took that from here because that was my original statistic. Then I went to the standard error that I calculated from running the stat key, which is 0.032. The formula says to multiply by 2. So I'll take a calculator and I'll take 0.275 and I'll add 2 of those. 0.032. So my first one, my upper is 339. 0.339. And then I'll go back and grab that same line, just go back up to that line, grab it again, and go back and insert a minus sign, and 0.211. In order to be part of this green bar situation right here, numbers had to hit from here to here. So when a test was run, and I ran another test, if it was below 211, it went red. If it was above 339, it went red. It missed the 95% confidence interval level. Question in Wiley, and these are questions 6. So for instance, using for mu, using x bar equal 25 with a margin error of 3. So it appears that what we're doing is we're writing a confidence interval level. I don't see the directions, but that's going to be my assumption right here. So again, I'm going to minimize back down so I can write 2 times for you. All right, so the first one here. And let me shrink this down a little so I can see the whole thing. There we go. So for mu, using x bar 25, remember x bar is our statistic. So since it's always going to be the stat, we only have 2 choices here. It's stat plus or minus 1 margin of error. And we'll also be able to substitute in, depending on what we have, 2 standard errors. So we have to read what we have. We have a margin of error. So for our margin of error, it's going to be 25 plus or minus a single value of 3. So it's going to be 22 to 28. So 22 to 28 would be given for the first question that you see. Next one. Wiley P-6Q says the same thing. For mu1 minus mu2, so difference in mean values, using x bar 1 and x bar 2, because you have to use x bar 1 and x bar 2 because that's the statistic for that. I got to scoot over a little bit. It says with a margin of error of 8. Okay, well, margin of error of 8 means that we're going to take 5 plus minus the margin of error of 8. You can see that for the negative of the 8, we're going to get a minus 3. And for the plus value, we're going to get a 13. My confidence interval level using my statistic is going to be somewhere between a negative 3 and a positive 13. For this one, it's somewhere going to be a 22 and a 28. Anywhere outside of there, it's not a plausible data value because it's outside of the 95% range. It doesn't mean that it can't take place. What it means is that it's not plausible, but it's still possible. Question 10. For a 95% CI, Fourier proportion is 0.72 to 0.79. Is the value given plausible for this? Okay, so let's go back and let's get some more here. So the first of all, the given parameters are 0.72 to 0.79. Those are my given parameters for my 95% CI. Our first given value is P0.85. Oops, I messed that up. 0.85. And I'll put a semicolon there that way. There's our first one. Okay, so first of all, if I look in between the 72 and the 79, 85 is not in there. 85 is outside of there. So the question would be, is this a plausible value? My assumption for this, assuming down at the bottom it tells us this, if we read it down here a little bit further, and I just saw that assuming that the sampling distribution is symmetric and bell-shaped, give the 95% CI, indicate the parameter being estimated for this. Okay, so we're going to utilize this after we're done with this here. So is this inside of this? And the answer is no, it's not inside of there. So, but is it possible? Sure, it's possible. So what we would say is no, it's not plausible because it's outside the CI. This value is outside of this value. There's your first one. Second one, P0.75. Okay, 0.75 is squarely inside of here. Yes, inside. It's that easy. And the last one, P0.7, I think. 0.7, yeah. No, outside, right? If given a CI and you're given a stat, is the stat inside or outside? So the last one here at the bottom, we're actually doing a little calculating, it looks like. Assuming that the sampling distribution is symmetrical and bell-shaped, give a 95% I, indicating the parameter being estimated. P hat is 0.2, so P hat is that, and the standard error is 0.04. So we have a P hat value of 0.32. We're going to add and subtract, it's a standard error this time, 2 times 0.04. Do that math. How about 0.24? And calculator says 0.40. There goes my 95% confidence interval level calculation. Perfect. All right, let's keep going. Common misinterpretations. Well, the first misinterpretation is that a 95% confidence interval level contains 95% of the data in the population, and that's not true. Remember, what we're trying to do is we're making a test And we're saying that that test will capture the true population parameter 95% of the time. That's what we're saying. Misinterpretation number 2. I'm 95% sure that the mean of the sample, we're not talking about a sample. This makes this one wrong right here. We are not talking about a sample. Will fall within 95% of the confidence interval for the mean. That's not what we're discussing. We're trying, again, we'll say the words all over again. We will capture the true population parameter 95% of the time within the CI. Misinterpretation number 3, the probability. As soon as it says probability, you can be done with it. This is not about probability. This is about capturing something within inside of a value. Let's see if we can look at question number 5 here and see what's going on here. Please give the following, let me see. Suppose a 95% CI for a mean commute time of workers in Atlanta is 27 to 31 minutes. Which of the following is the correct interpretation of the confidence interval level? So a couple things to make sure that you follow. First of all, this is a mean value. So we're saying that the mean, oops, can't do that very well, can I? We're saying that the mean value of these commuters, of all commuters in Atlanta, and is somewhere between here and here. Because remember, the population talks about all. So the question is, okay, which one says what I just said? So if we look at the top one, we're 95% sure that the mean commute time for all, I need all, and it's mean Atlanta workers is between 27.2 and 31. Well, that one looks like excellent. Let's look at the other ones, make sure. We are 95% sure the commute time for all Atlanta workers is between 27 and 31 minutes. Okay, the word mean does not pop into this one. It just says the commute time, not the mean commute time. We are 95% sure the mean commute time for the sample. See the word sample? Not going to happen. We are 95% sure the mean of what? We have no idea what the mean even is. That one's missing all kinds of stuff. So letter A is as good as we thought it was. So under our interpretation of a CI, it says let mu of E minus mu of N be the mean BMI for 2010 for all adults living in the U.S. who had exercised in the past 30 days, minus the mean BMI for 2010 adults living in the U.S. who had not exercised. So we're taking people who exercised, their mean, we're subtracting people who did exercise, their mean, and we're subtracting them and getting a value. A 95% confidence interval level for this is negative 1.947 to negative 1.83. So what is the interpretation of getting that negative value? Well, remember, if we're taking exercise averages and we're minusing non-exercise averages and we're getting negative numbers, what that means is that the BMI for the people who had exercised is below or under or less than the BMI for those people who did not exercise. And down below it says it is the adults living in the U.S. who had exercised is between 1.883 and 1.947, below those who had not exercised in the past 30 days. Don't write in your interpretations that it's negative numbers. Use words like below, under, less when you make that interpretation. Here goes another one. I'm not so sure we need this one, but so this is another interpretation of a negative. And what it goes up to say is that we have these male volunteers who average to take a look at a movie rate on a computer screen. And then what they did is they did volunteer of men who reported playing action video games. Okay. 95% confidence interval level for the mean response time. There it is right there. Mean response time for the players was negative 1.8 to negative 1.2 seconds, while 95% mean accuracy for game playing minus mean accuracy for non-players is negative 4.2 to positive 5.8. Okay, so what it is we're going to interpret what a negative actually means within here. Is it likely that game players and non-game players are basically the same in response time? If not, which group is faster? Okay, well, it's not likely that they have the same because they have a very, very different confidence interval level from -4.2 to -5.8 when we talk about that. And the game players are obviously faster because they're below. They're -1.8 to -1.2 faster, or their mean response time, so they would be faster. Is it likely that the game players and non-game players are basically the same in accuracy? If not, which group? Those two groups are basically the same when you look at them. For both questions, choose the correct answer from the list below. And that was just simply what I was choosing from. And I did that just based on the reflection of what took place here and what took place here. And by all means, go back in and go try that one and go look at that one too. But that'll give you some good guidelines for when you're working towards that question. All right, so let's see if we can get this one done. And then I think that should be a good place for us to stop with you. So it says here that we have a response of 2,625 U.S. adults were asked whether they agree or disagree. There's only one true love. And then response to the gender and participants is shown in Table 1. Use the information in the table to construct a 95% confidence interval level for the difference in the proportions who agree. Okay, so hold on, I got to underline that. So we need the difference in proportions who agree between males and females using the fact that the standard error, so that we're given a standard error of 0.018. Okay, so we have to do a little bit of calculating here. So first of all, we need agreement. So we need the males who agree right here. We need the females who agree right here. And that's going to be based out of their totals, because this is out of the males who agree and out of the females who agree. So let's get a place where we can work here, okay? And let's change this one into, let's make it so we can see what we're doing here. Let's make that one happen, and let's make that one happen, and let's shrink this one down. Okay. So first of all, let's get the proportion p hat, right, of males. Let's do that first. So the proportion of males is 372 over 1,213. Let's get a decimal value, 0.307. Let's get the p hat value for the females. And those were 363 out of 1,412. 0.257. Okay, our statistic, if we read back over here on the left-hand side, the difference in the proportion who agree between male and female. That means we need the proportion p hat of male minus the proportional p hat of female. We need 0.307 minus 0.257, which is going to be 0.05. So this is my actual statistic that I'm referencing right here. So now for the 95% CI, I'm going to take the statistic. I'm going to add and subtract either one measurement error or two standard errors, but they gave me a standard error. So it's going to be two standard errors of 0.018. So I have a value of 0.014. There's my lower boundary of my confidence interval level. And I have 0.086 for my upper. Somewhere between here and here is what we feel will happen in the true population parameter. It goes on to ask a question at the bottom over here. So we gave the CI. We did this. Is it plausible there's no difference? Okay, well, what does no difference mean? If I were to calculate physically that p hat of male minus p hat of female gave 0, no difference. There is no difference between the two. You are exactly the same as me, and I give you 0. Okay, well, refer back to here. This was the CI. 0 is not inside of the CI. So therefore, our response to this value has to be that it's not plausible because it's not in the CI. The answer is no, not in the CI. And we should actually say 0 is not in the CI. Beautiful. I think I'm going to leave this one for you. That's a good question, Wiley, but this one sets up exactly the same as the way I just set this one up. The only difference is I had to work from a table, and in this one, you can just pull the numbers out from the percentiles. Summary. To create a 95% CI for an interval, take many random samples from a population and compute the sample statistic. I did that here. Remember? Stat key, went to the mean. Doesn't matter what I'm working on. I pick my own numbers. I do what I have to do. I run many samples, remember? And I get this standard error. When I get this standard error is what I use, this SE. This is 2 times this value plus or minus this mean. Because remember, we're working from the sample statistic that we have. We compute the standard error. Excuse me. I had to change my mic there. We compute the standard error from the sample. We use the standard deviation of all the statistics, and we call that the standard error. We use the statistic plus 2 times the standard error, or we use the statistic plus or minus the actual margin of error if known. If we know the margin of error, we always use that. Because if the margin of error is given, we have a little more insight than we do. Because remember, when we're running the standard error, we're actually doing mathematical calculations that can be, remember, slightly off. They can change. They cannot be the same. If I come back here, 9.282, well, if I reset all this and I run it again, you'll see that it's not 9.872. It's not the same. I have a standard error, which is different. Now, the more I run, the better I get. But look, it's different than what it was just a minute ago. We know that happens, and we know that there's a small amount of error. But remember, that's part of the calculation. That's part of the statistical measurement. We had a small problem. In reality, we only have actually one sample. We don't have many samples. So we're going to use some techniques in the next one, and we're going to talk about how those additional techniques create all of the data that we need. When you come back, we will be moving into section 3.3, getting incredibly close to the end of chapter 3 itself. Have a nice time, and I'll see you then.